We continue our discussion on Einstein and special theory of relativity. Today we will consider the consequences of special theory of relativity, and also we will discuss a little bit of life history of the great physicist Albert Einstein. Now, as we showed last time that the mass of a particle is given by m0, which is the known as the rest mass of the particle, that is the mass of the particle in which in the frame where the particle is at rest, divided by 1 minus u square by c square. So, therefore, the kinetic energy of a particle of rest mass m will be given by m c square minus m naught c square. And as I mentioned, as we derived that m is equal to m 0 divided by 1 over under root 1 minus u square by c square. So, this is the expression for the kinetic energy of the particle. If the speed of the particle is very small compared to c, which is the speed of light in free space, as is normally the case, then I can make a binomial expansion of u square by c square, and I will get for the Lorentz factor 1 plus u square by 2 c square. If I substitute this in this expression, then 1 and 1 cancel out, and we will get for the kinetic energy half m 0 u square. This is the non-relativistic expression for the kinetic energy of a particle of mass m 0. So, in general, if the velocity is not very small, then the correct expression for the kinetic energy is given by m naught c square, the Lorentz factor gamma minus 1. Now, if we consider a body whose rest mass is 50 kilograms, and if we make it move with an enormous velocity, which is 0.9 times the velocity of light in free space, this is really an enormous velocity. The Lorentz factor you can calculate 1 minus 0.9 whole square, 1 minus 0.81, and if you do the simple numerical calculation, you will get a factor which is of the order of 2.3. So, therefore, 2.3 minus 1 is 1.3, m 0 is 50 kilograms, and the c square is 3 into 10 to the power of 8 meters per second. So, this corresponds to an energy of 6 into 10 to the power of 18 joules. This is an enormous amount of energy. This is an enormous amount of energy, and simple calculations will show that this amount of energy will be generated if a 100 megawatt power station will generate this amount of energy in a time period of about 2000 years. So, therefore, to accelerate a particle or a mass of 50 kilograms. The average human mass of a man is about 50 to 60 kilograms, to a velocity which is 90% of that of the speed of light, requires an enormous amount of energy. Now, continuing with our expression for total energy E. So, we have E is equal to E square C is 4, and so I do a simple manipulation, and m square is equal to m 0 square C 4 divided by 1 minus u square by C square, and then for the factor 1 I add and subtract u square by C square. So, I bracket this 1 minus u square by C square cancel out, and this quantity is the momentum multiplied by C whole square. So, I get the expression E square is equal to m 0 square C 4 plus p square C square. So, we have been able to derive the expression for the total energy E, which is equal to E square is equal to m 0 square C square C 4 plus p square C square. For the photon, the rest mass of the photon is 0, thus E square is equal to p square C square, and therefore, E is equal to p c, and so therefore, p is equal to E by c, and E, as we know from the Einstein's equation, is equal to h times nu. So, we get the momentum of the photon is given by h nu by c. So, let me digress here for a moment and go to one of his other papers, that is, in which he introduced the concept of the photon. Before we do that, let me tell you what is a wave. A wave is a propagation of a disturbance. So, in this slide, to show that there is a pin, a sharp needle, which is vibrating up and down on a calm pool of water, and this results in the emanation of waves, in this case circular waves, and the disturbance propagates outwards. The water molecules transfer energy from one molecule to the other. The water molecules themselves do not move outwards, they just transfer the energy. The medium is necessary for the transport of the wave from one place to the other. A wave phenomenon is associated with the phenomenon of interference, which is based on the superposition principle, according to which the resultant displacement at a particular point produced by a number of waves is the vector sum of the displacements produced by each one of the disturbances. And therefore, if I have suppose a water molecule which is moving up and down with an amplitude a, and the time displacement is given by a cos omega t, and let us suppose from another source you have the displacement a cos omega t, then the two will add up to produce a maximum, and the displacement as a function of time will become 2a cos omega t. If one of the sources produces a displacement a cos omega t and the other produces a displacement minus a cos omega t, then the resultant will be a vector sum which is 0, and you will obtain what is known as a minimum intensity. And this is the actual interference pattern produced from two pinpoint sources, two needles vibrating up and down on a calm pool of water. Each sends out waves and they interfere. So, the resultant displacement produced will be the vector sum of the displacements produced by each one of them separately, and when they are in phase, it will produce a bright point, a high amplitude, and when they are completely out of phase, it will produce a dark point, that is the minimum intensity. And this is a beautiful manifestation of the superposition principle, and this is the phenomenon of interference. Now, there was a beautiful experiment that was done by Thomas Young in 1801, in which he allowed light to pass through two pinholes. Now, each pinhole sends out circular waves, so spherical waves, and they interfered, and it produced very sharp dark and bright fringes. So, therefore, this experiment demonstrated the phenomenon of interference and cannot be explained by means of a simple particle model of light. The particle model of light, which was originally put forward by Rene Descartes and subsequently put forward by Isaac Newton in his famous book Optics, then if I assume a particle model of light, then the particle has to go either through hole number 1 or through hole number 2, and when both the holes are open, the intensities will add up. On the other hand, when both the holes are open, there are regions where there is complete darkness. This cannot be explained on the basis of a simple particle model, and so therefore, the interference phenomenon, as was observed by Thomas Young in this very famous experiment, proved unequivocally that light was indeed a wave phenomenon. He measured the wavelength of light, and he found it to be of the order of half a micron, and this established the wave nature of light. If once the wave nature of light was established, the phenomenon of diffraction was also observed, which is a manifestation of the wave nature of light, and polarization was also observed. So, it was by around 1820 or so, it was very well established that light was indeed a wave. Then the main question was that if light was a wave, then how could it propagate through vacuum? Because as we know, a wave, a classical wave, requires a medium to transport energy from one place to the other. So, this bothered the physicist, and this was an important field of research during the early parts of the 19th century. The concept of ether, an all pervading ether, was put forward, and people tried to find out the properties of this ether. It was Maxwell who in the middle of the 19th century put forward, wrote down again the laws of electricity and magnetism, and from the laws of electricity and magnetism he derived a wave equation, and from this wave equation he found out that the velocity of these electromagnetic waves was equal to 3 into 10 to the power of 8 meters per second, and this value was so close to the velocity of light as measured by Fizeau, by the French physicist Fizeau, that he made the very famous statement that light must be an electromagnetic wave. This is said to be one of the greatest syntheses in the development of science. So, around 1864, James Clerk Maxwell predicted the existence of electromagnetic waves. I insist that, please note that he predicted the existence of electromagnetic waves. The electromagnetic waves were subsequently observed by Heinrich Hertz around 1887 or 1888, and Maxwell said that light itself is an electromagnetic wave. Associated with the light wave, there is an electric field and there is an oscillating magnetic field. This is an electric field propagating in the x direction, which has a y component of the electric field and a z component of it. This such a wave is known as a plane polarized wave propagating in the x direction with a velocity which is equal to omega by k, and in free space v is equal to c. So, physically what is happening is that a changing electric field produces a changing magnetic field, and that is the concept of the displacement current that was introduced by Maxwell. And Faraday's law said that a changing magnetic field will produce a changing electric field. So, when the electromagnetic fields are created, a changing electric field will create a changing magnetic field, a changing magnetic field will produce a changing electric field. That is how the electromagnetic waves propagate through free space. So, it is the propagation of the fields associated with a light wave, and this was first clearly put forward by Maxwell around 1864. And as we now know that from gamma rays to X-rays, ultraviolet and infrared, microwave and radio waves, they are all part of the electromagnetic spectrum. They are all governed by Maxwell's equations. The visible portion that is sensitive to the retina of our eye, from the blue region to the red region, occupies a tiny region in the entire electromagnetic spectrum. The only difference is that gamma rays are associated with very high frequencies, then come X-rays, then come ultraviolet, then come visible, and as we go to infrared or microwave or radio waves, the frequencies become smaller and smaller and the wavelengths become larger and larger. All these travel with an identical velocity in vacuum, and this is the entire electromagnetic spectrum, which are solutions of the Maxwell's equation. So, Max Planck had said, Max Planck was an outstanding physicist. He had said that Maxwell's theory remains for all time one of the greatest triumphs of human intellectual endeavor. On the background of this, so around the turn of the century, around the turn of the 19th century, Maxwell's electromagnetic theory was very well established. People thought that they knew what light really was and how light could propagate through vacuum and in the form of electromagnetic fields, and the interaction of light with matter was the origin of refractive index, the calculation of the refractive index, the propagation of beams in matter, reflection and refraction, everything could be explained on the basis of Maxwell's electromagnetic theory. So, one thought that probably one branch of science was completely understood until around the beginning of the 20th century. There was this famous experiment on photoelectric effect, which I will describe in a few minutes, was discovered, and Einstein developed in one of his papers, one of his 1905 papers, that there are certain experiments. He said there are certain experiments which tend to show that the absorption and emission of light appears in the form of quanta of energy. So, in 1905, Einstein put forward the hypothesis that light consists of quanta of energy, and these quanta of energy later was termed as photons, and this quantum of energy is given by E is equal to h nu, where h is the Planck's constant and nu is the frequency. This wave particle duality eventually led to the development of quantum theory. In his 1905 paper, which I had referred earlier, Einstein wrote, and let us read this little carefully. When a light ray starting from a point is propagated, the energy is not continuously distributed over an ever increasing volume, but it consists of a finite number of energy quanta localized in space, which move without being divided and which can be absorbed or emitted only as a whole. Albert Folsing, a great biographer, in a book entitled Albert Einstein, wrote that this is the most revolutionary sentence written by a physicist of the 20th century. So, on the background of the electromagnetic waves, he put forward the corpuscular model of light. He put forward the corpuscular model of light. Now, this created a lot of problems, because the corpuscular model of light was put forward by Newton, and before that by René Descartes, but then it was overshadowed by the wave theory. Now, we have this corpuscular model, and on top of that we have interference and diffraction experiments. How do we reconcile to that? And that led to the development of quantum theory. The experiment that he explained in his 1905 paper was the famous photoelectric effect experiment, which most of you would be knowing, and this experiment, according to this experiment, when incident light when light is incident on a metal surface like cesium or copper or sodium, and if the frequency is larger than the critical frequency, then photoelectrons are emitted. And the maximum energy, and by applying a suitable voltage, these electrons can be collected by the plate P2. This equation is known as the Einstein equation, and this equation was first put forward by Einstein in his 1905 paper, in which he showed that the maximum kinetic energy of the electron is equal to h nu, the energy of the photon, minus the work function, minus the minimum amount of energy required to take the electron out of the metal. So, if we plot the maximum kinetic energy for cesium, sodium and copper, then as a function of frequency, then it is almost a straight line, very accurately a straight line, but there is no emission of electrons below a certain critical frequency. Now, photoelectric effect as such can be understood by using wave theory, because a wave carries energy, and so therefore, we can assume that this wave transfers a certain amount of energy to eject the electrons out of the metal. But the main characteristic of this experiment, which I just now said, that there is a critical frequency. No matter how intense the light is, if the frequency is less than a critical frequency, then no emission of electrons take place. Classical wave theory would say that if the intensity is large enough, then there is a large amount of energy associated with the electromagnetic wave, and it should be able to eject out the electrons. But the experiment showed, and Einstein's photoelectric equation also showed, that there is a critical frequency. So, I repeat, no matter how intense the light beam is, unless the frequency is greater than a critical frequency, no electrons will be emitted, and this cannot be explained on the basis of Maxwell's electromagnetic theory. And this is what this slide shows, that for all the metals there is a critical frequency. These are the original experiments of Robert Millikan, who did very careful measurement and established the Einstein's photoelectric equation. And Robert Millikan, who himself got the Nobel Prize for this work, he wrote that Einstein's equation is one of exact validity, always within the present small limits of experimental error, and of very general applicability, is perhaps the most conspicuous achievement of experimental physics during the past decade. This is a photograph of Michelson. Einstein is standing in the middle, and Millikan, who carried out this experiment. Around the same period of time, as you all know, the electron was discovered. J. Thomson discovered the electron, for which he got the Nobel Prize, and this was in the year 1897. And electron, as we all know, has a very well defined mass. It has a mass which is known to 9 decimal or 10 decimal places. It has a charge which is also determined experimentally to 10 decimal places. So, we visualize the electron can be deflected by an electric field, it can be deflected by a magnetic field, it can be detected. It is always detected as one whole electron and never half of an electron. So, on the back of our mind, we think it is probably a tiny particle which can be deflected by electric and magnetic fields. But later it showed that it also has wave-like. One can carry out experiments which shows the wave nature of electrons, not only with electrons, but with protons, with neutrons, and with everything that you know of. So, this wave particle duality, let me give you the answer first. So, then you ask yourself, is the proton or the electron a wave or particle? Many books write that it is both a wave and a particle. This is not quite right. The correct answer is, it is neither a wave nor a particle. You cannot understand it in a classical way. So, we will try to understand it only very partially through quantum theory. So, Louis de Broglie, who also got the Nobel Prize for his contribution to wave particle duality, he wrote that I was convinced that the wave particle duality discovered by Einstein in his theory of light quanta, that is his 1905 paper, was absolutely general and extended to all of the physical world. And it seemed certain to me, therefore, that the propagation of a wave is associated with the motion of a particle of any sort, photon, electron, proton or any other. What he tried to say was that the wave particle duality is not only with light, but also should be with electrons, protons, anything that you can think of. And the wave particle duality led eventually to the development of quantum mechanics. And once again, it was in 1905 that first Einstein had introduced the concept of the photon and therefore, the wave particle duality itself. So, it was Einstein's paper which eventually led to the development of quantum theory. So, I will not go into the details of this, but I will just mention that the wave particle duality eventually led to what is known as the Schrödinger equation, and this equation was derived by Schrödinger. And so, therefore, if you ask me that whether an electron is described, a non-relativistic electron is described accurately by this Schrödinger equation, and if you ask me whether it is a particle or a wave, the correct answer is, it is neither, but it is described by a wave function psi, by which in general will be complex. So, it is described by a wave function psi, and the physical interpretation was put forward by Max Born in 1926 itself. He formulated the now standard interpretation of the probability density function for psi star psi, for which he was awarded the 1954 Nobel Prize in Physics some 3 decades later, that psi star psi d tau represents the probability of the finding the electron in the volume d tau. And using quantum mechanics and using the solution of the Schrödinger equation, then we can write down that if we consider a wave function which is confined in a region of the order of the slit width, then by solving the Schrödinger equation, one can show that it implies that by confining the electron in a region of the order of b, a momentum is imparted by the slit system, and the probability of the momentum, probability that the momentum lies between px and px plus dpx, is proportional to sine square beta by beta square, where beta is equal to pi times b is the width of the slit, sin theta is the angle of diffraction, and lambda is the de Broglie wavelength. So, this is my single slit diffraction pattern that you can derive from a simple wave model of light. So, therefore, if you carry out this experiment, with a source which is very far away and a very weak source, so that one electron comes in or one proton comes in or one neutron comes in and then another neutron. So, you pass through a slit, the slit imparts a momentum in the x direction, and there is a probability distribution associated. One electron may arrive here, one electron may arrive here, one electron may arrive here. You can only predict the probability of arrival in a certain region. You cannot predict for sure where it will arrive. This is the major concept in quantum mechanics. Physics has ceased to be deterministic. You cannot predict where an electron will arrive on the screen. You can only predict the probability of arrival in a particular region. And so, therefore, this is a tremendous deviation from the concepts of classical physics, to which Einstein could never reconcile. And this is an experiment, as you all know, this is the Young's double hole experiment, which I mentioned some time back, that I have a source of electrons, let us suppose. It emits, we can assume waves, and then it passes through two holes, and then it produces the interference pattern. Now, you do this experiment with electrons. On the screen p p prime, you will observe only one electron or none. This is the probability distribution. If you did with 1 or 2 electrons, where will it arrive? I do not know. I cannot predict. Not that I cannot predict, no one can predict. But if you did this experiment with billions of electrons, then slowly the interference pattern will evolve. And this, if you solve the Schrodinger equation, then you can get a probability distribution for corresponding to this product of the single slit diffraction pattern and the 2-point interference pattern. And this explains the quantum nature of the electrons. That here on the top slide corresponds to 10 electrons, experiment carried out with 10 electrons. Where they will arrive, one can never predict. As you increase the number of electrons, slowly the interference pattern, the double slit interference pattern will slowly emerge. So, once again, quantum mechanics allows you to predict the probability distribution of where the electrons will arrive. It cannot say for sure that where it will arrive, in which region will it arrive precisely. If you carried out the measurement with 1 or 2 electrons, the experiment with 1 or 2 electrons, where will it arrive, you do not know. But if you carried out the experiment with a billion electrons, then slowly, because of the probability distribution, slowly the interference pattern, as I had shown in the previous slide, will appear. Now, on the other hand, if it were classical wave theory, then the interference pattern would have looked something like this for all intensities. You see, the intensities may become weaker, but the contrast may become smaller, but the intensity will be something like this even with a very faint source of light. The very fact that we get a granular pattern shows the quantum nature, the particle nature of the electron, and the fact that it arrives with certain probability distribution is a manifestation of the quantum phenomenon. Let me give you another example. Let me consider that this is a radioactive solid. Now, radioactive solid means something like uranium, which has a certain half-life. Let us suppose the half-life is, usually the half-life of uranium is millions of years, but let us suppose that it is 1 day. What does the concept of half-life imply? The concept of half-life implies that if the half-life is 1 day, and let us suppose if we have 10,000 atoms in the solid, then in 1 day 5,000 will disintegrate. In the next 1 day, in the second day, about 2,500 will decay. But you cannot predict which one will decay. So, some atoms will disintegrate in the next minute, and some atoms will stay on for days. So, identical atoms behave differently. They are governed by probabilities. And once again, physics has ceased to be deterministic. You cannot predict what will happen in a given circumstance. You can only predict the probability of occurrence of different events. So, similarly, this is the photograph of a young girl. This corresponds to 3000 photons, and the last figure, the F, corresponds to 28 million photons. So, we can say that in this region where there is white, the probability of arrival is large. In this region, the probability of arrival is extremely small. But where an individual photon will arrive, one can never say. When you detect the photons, it is either one photon or no photons. So, So, now in this experiment I have tried to show the diffraction pattern of aluminum foil produced by X-rays on the left and by electrons. So, whatever the X-rays are, whatever X particle wave or whatever you may like to call them, they are the same. They are both they both show wave particle duality. Similarly, I have let me mention one more thing, that how do we explain this, that this interference phenomenon, when you write the Schrodinger equation, then you have a wave function which is present here in the hole slit, in the hole S1 and hole S2. So, that the electron passes through both the holes simultaneously. This is a quantum concept, that electron passes through both the holes simultaneously. It is here as well as there, but if when you try to make a measurement, it is either here or there. So, the electron or the photon or the neutron or the alpha particle interferes with itself to produce a probability distribution something like this. In this experiment, most of you are familiar, this is a beam splitter, that is a partially reflecting plate. So, light beam comes in and it gets partially reflected and partially transmitted, and then they are reflected by the mirror, and these come back and they interfere. They produce a beautiful interference pattern. For those who are familiar, this is known as the Michelson interferometer experiment. So, then how do we explain this on the granular picture? That how do we explain this on the basis of photons? Now, I have a plate like this. A light beam comes in and gets reflected and transmitted. So, if I ask you that, let us suppose there are 1000 photons that are coming, then you will probably naively say that 500 will go this way, 500 will go this way. No, that is not a right answer. The right answer is that if I have a photon coming in, falling on a plate, then the photon is reflected as well as transmitted. It is in both the beams. It is here as well as there. It interferes with itself. This is very beautifully described in one of the most famous books on quantum mechanics by Professor Dirac, Principles of Quantum Mechanics, that the photon is in a state which is in this beam as well as in this beam. If you make a measurement as to which beam it has passed through, then it is either here or there, but the process of measurement will destroy the interference pattern. The process of measurement will destroy the interference pattern. So, similarly, in our experiment using the double hole, the electron or the photon passes through both the slits simultaneously. If you made a measurement as to which hole it has passed through, it will be either through that hole, one hole or the other, but the process of measurement will destroy the interference pattern. So, Richard Feynman, in his famous Feynman lectures on physics, he writes, as you know that Richard Feynman received the Nobel Prize for his very significant contributions in quantum electrodynamics. He writes, it would be impossible to predict what would happen. We can only predict the odds. This would mean, if it were true, that physics has given up on the problem of trying to predict exactly what will happen in a definite circumstance. Yes, physics has given up. We do not know how to predict what would happen in a given circumstance, and we believe now that it is impossible, that the only thing that can be predicted is the probability of different events. So, what he is trying to say is that physics has ceased to be deterministic. It is governed by probability laws. So, Einstein told Max Born, Einstein could never reconcile to this indeterministic nature of physics. He wrote that I find the idea quite intolerable that an electron exposed to radiation should choose of its own free will not only its moment to jump off, but also its direction. He wrote to Max Born that quantum mechanics is very impressive, but an inner voice tells me that it is not yet the real thing. The theory produces a good deal, but hardly brings us closer to the secret of the old one. I am at all events convinced that God does not play dice, that God does not play with probabilities. So, through this quotation, this is a very famous quotation, and people say that Einstein did believe in God, but he believed in a deterministic God. So, Niels Bohr's response is somewhat less well known, and he would tell that Einstein stopped telling God what to do. On April 24, 1921, Rabbi Herbert Goldstein of the Institutional Synagogue in New York had sent a telegram to Albert Einstein and asked the following question: do you believe in God? To which Einstein replied in another telegram that I believe in Spinoza's God, who reveals himself in the ordinary harmony of what exists, not in a God who concerns himself with fates and actions of human beings. This is quoted from a very famous book, Albert Einstein, Philosopher Scientist. So, Einstein did believe in God, but he did not believe the non-deterministic nature that is predicted by quantum mechanics. I may mention that all experiments till now prove the validity of quantum mechanics. Quantum mechanics is said to be one of the most accurate sciences. Whatever it has predicted, one has found true, and therefore, things are indeed indeterministic in nature. Physics has ceased to be deterministic. Einstein had apparently said that we see a universe marvelously arranged and obeying certain laws, but only dimly understand these laws. Our limited minds cannot grasp the mysterious force that moves the constellation. I continue the discussion and would like to mention about his getting the Nobel Prize. Wilhelm Ostwald, who won the 1909 Nobel Prize for Chemistry, was the first to nominate Einstein for the 1910 Nobel Prize in Physics for his theory of relativity. His special theory of relativity came in 1905. But there was so much of heated discussion, and there was also a lot of prejudice, that even in 1920 the members of the committee did neither believe in the concept of the photon nor in the theory of relativity, and did not trust the experimental observations confirming the general theory of relativity. After a lot of arguments, the 1920 Nobel Prize in Physics went to Charles Guillaume in recognition of the services he has rendered to precision measurements in physics by his discovery of anomalies in nickel steel alloys. Even those physicists who were against the theory of relativity and advocated for Einstein not to get the Nobel Prize were surprised that Guillaume's mediocre work resulted in the award of the Nobel Prize, and this created a furor. And as I had mentioned in the previous lecture, you see, in 1905 he wrote 5 papers, and many people feel that each one of those papers, special theory of relativity, theory of light quantum, theory of Brownian motion, which started the statistical physics, each was worth a Nobel Prize. Then he put forward the general theory of relativity, which is still today considered as a masterpiece. And it was verified in 1919 in an experiment which was conducted by Arthur Eddington. But even then, people would not give him the Nobel Prize, and I will tell you the reason for that. You think there is politics here, there is politics everywhere. There is a very beautiful book by Carl Friedman, and the title of the book is The Politics of Excellence, the politics that goes behind the award of the Nobel Prize. It is a very detailed analysis as to why even very competent people are often the work of them are not taken care of, and sometimes a mediocre person ends up getting the famous example is that of Mahatma Gandhi. He was awarded the Nobel, he was nominated for the Nobel Prize 5 times, but he never got the Nobel Prize. His disciples like Martin Luther King, Dalai Lama and Nelson Mandela got the Nobel Prize. Apparently, the Swedish Academy has said that it was a mistake not to give the Nobel Prize to Mahatma Gandhi. In 1921, Alvar Gullstrand, a very distinguished member of the Swedish Academy, had apparently said, Einstein must never receive a Nobel Prize, even if the whole world demands it. For the 1921 Nobel Prize in Physics, there was so much of heated discussion that the prize was withheld. This caused embarrassment to the Swedish Academy and a question mark on the Nobel Prize itself. Indeed, in 1922, when the Swedish Academy decided to award the 1921 Nobel Prize in Physics, it was not for his theory of relativity, nor for his concept of the light quantum. It was for the discovery of the law of photoelectric effect. So, it was for the discovery of this equation that he was awarded the Nobel Prize. Why such a delay? And the book that I was referring to by Carl Friedman, he writes, he has made a very, very detailed analysis of the politics that goes on into the award of the Nobel Prize. He writes that a prejudice against pacifists, Jews, and most of all theoretical physics. Swedish physicists held precision measurement as the highest goal for their discipline. But eventually in 1922, Einstein was awarded the 1921 Nobel Prize in Physics for the equation describing the law of photoelectric effect. And it is still argued that why he was never given the second Nobel Prize for his theory of relativity. Let me continue the discussion. I am saying that this Nobel Prize was awarded in 1922. Actually, he got the 1921 Nobel Prize. And in 1924, the Indian physicist Satyendranath Bose, then at Dhaka University, rewrote Planck's law by assuming that light was a gas of indistinguishable particles. So, what do I mean by that? If I have two particles, and let us suppose I want to distribute in two energy levels E1 and E2, then if they are distinguishable, like one is a red marble and the other is a blue marble, then I can distribute this in four different ways. The red up in E2, the blue in E1 and so on. On the other hand, if the particles are indistinguishable, then you can distribute in only three ways. This led, so what he did was, the history goes something like this, that Bose was first to introduce the concept of indistinguishability of particles. He sent that paper to Philosophical Magazine, which is usually referred as Philmag. The Philmag turned it down. So, he sent the paper to Albert Einstein, and he said that if you feel that the paper is good enough, you translate it into German and submit it to Zeitschrift für Physik. Einstein saw immediately the greatness of the paper. He translated to German himself and he sent it to Zeitschrift für Physik, and he wrote that Bose's derivation of Planck's formula appears to me to be an important step forward. The method used here gives also the quantum theory of an ideal gas, as I shall show elsewhere. So, what Einstein did was that he extended Bose's analysis. Bose applied it to photons and Einstein extended the analysis to atoms, and he predicted what came to be known as the Bose-Einstein condensation, for which the 2001 Nobel Prize in Physics was given to Eric Cornell, Wolfgang Ketterle and Carl Wieman for the achievement of the Bose-Einstein condensation in dilute gases of alkali atoms and for early fundamental studies of the properties of the condensates. Unfortunately, Satyendranath Bose never got the Nobel Prize. Einstein had also worked closely with Tagore, had a lot of discussions with him, and he argued on topics like the difference between melody and harmony. There are various websites on which the discussion appears. Max Planck presented Einstein with the Max Planck Medal in Berlin on June 28, 1929 for extraordinary achievements in theoretical physics. In the next hour, what I will be doing is considering the first paper of special theory of relativity that was put forward by Einstein, in which he said that light always propagates in free space with a particular velocity irrespective of the motion of the source. What it physically implies is, let us suppose I am inside a train and you are on the platform. So, with respect to you, I am moving with a velocity, let us suppose 100 kilometers per hour. So, I am inside the train and you are on the platform and I am moving with a velocity 100 kilometers per hour. I have a tennis ball or a cricket ball in my hand, and along the length of the train, I throw the ball with a velocity, let us suppose 20 kilometers per hour. So, it is a long train. So, I throw a tennis ball along the length of the train with a velocity 20 kilometers per hour. Then with respect to you, the ball will appear to be moving with a velocity 120 kilometers per hour, and the tennis ball will reach the destination before I do. So, once again, I am inside a train and I am moving with respect to you with a velocity 100 kilometers per hour. Along the length of the train, I throw a tennis ball with a velocity 20 kilometers per hour. Then with respect to you, the tennis ball will be moving with a velocity 120 kilometers per hour. Now, I consider that let us suppose this is a laser pointer. I switch it on and switch it off, and I produce a light pulse. I am still inside the moving train, and therefore, the light pulse moves away from me with a velocity 3 into 10 to the power of 8 meters per second, that is 300,000 kilometers per second. What Einstein said was that not only with respect to me, but also with respect to the person on the platform, the light moves with the same speed, that the speed of light in free space is a constant. This remarkable statement was put forward by Albert Einstein in his 1905 paper. And what is the consequence of that? Let us suppose I now hold the laser pointer vertically, I am still inside the moving train, and I switch on the laser pointer and switch it off. The light pulse goes up and there is a mirror on the top and it comes back. So, there is a laser pointer here and there is a tiny detector here. So, the light pulse goes up and it comes down. So, there is a certain amount of time that the light pulse takes. Let us suppose it takes say 1 second, that means the mirror is really very far away, does not matter. So, it is 1 second that the light pulse takes to go up and come down. On the other hand, for you who is standing on the platform, when the light pulse is emitted, it is emitted from this point. By the time it hits the mirror, it has moved a certain lateral distance, and then by the time it is detected by the detector, the whole train has moved. So, with respect to you, the light path takes a triangular path. So, let me show you that I am inside this train, and there is a light pulse which I send, and there is a mirror here, and it gets reflected, and there is a detector here. So, what will be the time taken? This, if let us suppose this height is h, so delta t prime in this frame is 2h divided by c. On the other hand, when the instant this light pulse is emitted, the source is here. By the time it reaches the mirror, with respect to the person on the platform, it has come here. So, the light path takes a triangular path. So, let us suppose this is P, this is M, this is D. So, the light ray travels a path P, M, D with respect to the person on the platform. So, the time that time interval between the two events that is observed by the person on the platform is P m plus M d by C. And of course, because this is greater than this path, delta t is greater than delta t prime, and therefore, time is not absolute. This was one of the remarkable statements made by Einstein in his 1905 paper, that when I am traveling, the time interval between the two events, what are the two events? The lighting of the source, the laser pointer, I produce a light pulse, that is first event, and its subsequent detection. So, since both of them occur at the same space point, we say that this is the proper time between two intervals. But for you who is standing on the platform, the two events occur at two different space points, and that is known as the improper time. But the time interval between the two events that you will measure will be slightly more. And what I am going to explain to you in the next lecture will be that if I go very fast in this train and go to a distant place and then return, then whereas in my frame of reference I will think that I have taken only 1 year to come back, in your frame of reference it may be 10 years. Provided my velocity is extremely large and I am very far away, that I go to a destination which is very, very far away. So, this is usually known as the twin paradox. Actually, there is no paradox. It follows from the special theory of relativity that was put forward by Einstein, and it was confirmed experimentally in the year 1939 after the prediction that was made by Homi Bhabha. He suggested the experiment which can lead to the confirmation of the special theory of relativity, and the special theory of relativity was proved, and it was proved unambiguously that time gets dilated. And so, therefore, if we have if my twin who is on the platform to start with, when I come back I will be much younger to the twin. So, it is this concept that I am going to develop in the next lecture. Thank you.